Yeah, colleagues, we are starting to second session today, and we continue now with first, report from the experience of the BIT1 modeling by Simon Ra. He's our very good PhD student and was quite successful in simulations. And so, floor for you, please.
Thank you. So as said, today I'm going to share with you my first experience with PIC modeling of the plasma sheath. So in this presentation, we will mainly see how can we obtain Maxwellian plasma in BIT1. We'll also observe the effects of the plasma sheath and of different types of collisions on the velocity distribution functions. And we'll also compare the values of potential drops and particle fluxes to the results from analytical formulas which rely on Maxwellian distribution. So at first, let's briefly remind ourselves of what is the plasma sheath. So when the plasma sheath gets
not sharing, and they go. Okay.
This one. Right. So the plasma sheath gets formed when plasma touches the wall. Because the electrons are much lighter than the ions, they also have quite higher velocities, and so go to the wall preferentially charged negatively with respect to the plasma potential, and this causes the creation of a potential drop, which then reflects the low velocity electrons away and attracts ions towards the wall until the equalization of the fluxes basically happens. So in this region of the potential drop, we also obtain a significant charge imbalance, and this region is what we call the plasma sheath. The edge of the sheath is usually taken as the point where the plasma flow towards the wall becomes sonic, so where the Mach number is equal to 1. And this potential drop we then also call the floating potential in case of floating wall conditions. If we add magnetic field with some inclination to the wall, the situation somewhat changes. Then the whole floating potential gets actually split into two different regions, into the magnetic pre-sheath, which is slightly further from the wall, and the Debye sheath, which is right next to the wall. So like further away from these, from this region, there's the usual pre-sheath, which is accelerating ions towards the sound speed parallel to the magnetic field, which is the condition that they reach at the magnetic pre-sheath entrance. Then inside the magnetic pre-sheath, they start to get accelerated in the direction perpendicular to the wall. And that is then the condition at the Debye sheath entrance. And then in the Debye sheath, we get the usual charge imbalance as previously we had. So just to get an idea of the kinds of length scales they were talking about, the Debye sheath is on the scale of the Debye length, while the magnetic pre-sheath is on the scale of the ion Lambda radius. So if we have a system of density about 10 to 19 per meter cubic, with temperature around 10 electron volts and magnetic field around 4 Tesla, then the Debye length is of the order of 5 micrometers, while the ion Lambda radius is about 100 micrometers. So that if we want to really simulate sheath, it should be sufficient to choose, say, just a few millimeters. So if we want to have both sheaths on both sides, plus some source region, we could suffice with about 1 centimeter system. So let's get to the first example, which is the unmagnetized plasma sheath. So here we have the 1 centimeter system absorbing walls on both sides, and in the center, we inject electrons and deuterium ions, Maxwellian distributed at 10 electron volts. So when we inject Maxwellian plasma, the plasma doesn't actually remain Maxwellian since the fast particles kind of quickly disappear from the region, while the slow particles keep building up. So the actual distribution is more something like Maxwellian divided by velocity. So in order to keep the distribution Maxwellian, we need some kind of collisions. However, at this length of the system and these chosen parameters, we don't get sufficient Coulombic collisionality. So in order to achieve Maxwellization, we can use the BIT1 feature, which is called heating. So in that case, when we turn it on, the simulated particles then collide with a reservoir of Maxwellian distributed particles at a target temperature, and they collide heat number of times on average. So these are still Coulombic collisions, so the frequency is proportional to 1 over v velocity cubed. So heat number of times really only applies to the particles moving at 1 thermal speed. The faster particles collide less, while the slower particles more. So we can now look at the effects on the electron velocity distribution functions near the right wall. So these are the electron velocity distribution functions. They are normalized to a unit area under the graph. Here, the negative velocities are away from the wall and the positive velocities towards the wall. In red, we have the Maxwellian corresponding to the recorded temperature, and the blue one is directly the distribution function, which is recorded by the BIT1 code. So here we have the case with heating 1. So we can see that we are really missing these higher velocity electrons, and we get a significant deviation from the Maxwellian distribution. Then as we increase the heating to about 300, we obtain quite a nice Maxwellization. So here we can observe this kind of a sudden cutoff of the distribution function. And this is exactly caused by the plasma sheath. Because if you remember, here close to the wall, we don't actually have any source of electrons, which means in principle, we should just have the electrons going towards the wall. So this backwards going part of the distribution is actually reflected by the plasma sheath potential. And these higher velocity electrons don't get reflected because they overcome the potential drop and get absorbed by the wall. And we can just kind of observe the same thing on 2D distribution functions. In the vertical axis, we have the X position. So this is the left wall, this is the right wall. And here we have the negative velocity, so this is moving towards the left wall, and here we are moving towards the right wall. So we can see that as we increase the heating, right, then the brighter colors are more spread out, so this means that we have more particles also at the higher velocities in the case of heating 300. This is exactly what I mentioned, that beyond this point, we're basically outside of the source region, so we don't really generate these backwards going electrons. Although we still have some backwards going electrons because they are getting reflected by the sheath potential drop. And we can see that actually much even higher velocity electrons are getting reflected in the case of the heating 300, because the heating means that we are getting more Maxwellian distribution, which means more higher velocity electrons, which causes the potential drop to increase and in turn reflect also slightly higher velocity electrons than before. We can observe also similar thing with the ions. Here in the case of heating 1, again, we see a bigger portion of much higher number of the slow particles, and when we increase the heating to about 300, we get a better spread of the velocities. And same thing can be again observed in the 2D case, where we get a better spread of the velocities. Here we can see kind of this inhomogeneity, but this is really only caused by the fact that at each point X, the distribution function is normalized to a unit surface under the graph. So since here there's the values are non-zero only on half of the system, obviously we are going to get a brighter area here. So it's just normalization effect. So next we can go to quantitative comparison. So here I'm given the result of the floating potential and the ion and electron wall fluxes is recorded by the BIT1 code for the heating 1, 50, and 300. And we can compare these values to differently obtained values. So we can go to the density and temperature as recorded by the BIT1 code and use formulas which rely on Maxwellian distributions in order to compute the floating potential and the wall fluxes. So these are the standard formulas which can be, for example, found in Stangby. So here in the parentheses, I give the relative error between these two values. So we can see that in the heating one, we have a very low potential drop and very high relative error. And as we increase the heating, the potential drop starts to increase since we're getting more of the higher velocity electrons. And the relative error also decreases. So we can see that when we get the good maxwellization, we really have very good agreement with the analytical formulas. The effect on the ions is much smaller since we don't really require them to be Maxwellian. That's not really usually the assumption inside the sheath. And in the case of the electrons, there's quite a large effect because the computation of their wall flux heavily depends on the floating potential. So next we can go to the magnetized plasma sheet. So we add a magnetic field at about 85-degree inclination from the normal, so it's this angle. And since the electrons and ions are moving along the magnetic field lines, this effectively increases the system size about 11 times. So this already gives us kind of sufficient length of the system to have good Coulomb collisionality. So we're going to compare two cases, both with heating one, but one with and one without Coulomb collisions. So now I can probably speed up because essentially the same idea as before. So on the left, without Coulomb collisions, in the case of electrons, we're missing higher velocity particles. We turn the Coulomb collisions on and we get a nice maxwellization. Now we can observe slight difference in the case of the Coulomb collisions. We actually get kind of a gradual increase in the number of high velocity electrons going away from the wall, which is clearly caused by the fact that now the whole place basically, we can have collisions, and so the further away we are, the more the high velocity part of the Maxwellian is getting replenished. We can see, again, very nice effect of the Coulomb collisions also on the ion distribution functions, where we get a very good maxwellization when we turn the Coulomb collisions on. And in this case, we can observe that we now get also backwards going ions outside of the source region as a result of the Coulomb collisions. So in the case of the inclusion of magnetic field, we can also compare the potential drop in a Debye sheath. We can see that, again, when we turn the Coulomb collisions on, we get much better agreement. The relative error is still quite high in the case of the Debye sheath because the entrance was determined by the Mach number being unity, but there was a very high gradient in this case, so it's quite high error. So let's go to the last case, which is including recycling in the plasma sheath. So in this case, when the ions hit the wall, we release neutrals, Maxwellian distributed at 2 electron volts. So just to know that in this case, it is released so that the end result is a Maxwellian distribution, which is quite different from the central source. It could be noted that they are about 5 times colder than the ions, which is going to be quite relevant. We're going to compare the effect of two sets of collisions. The first collision are between electrons and neutrals. These include elastic, excitation, and ionization collisions, and then between ions and neutrals, which include elastic and charge exchange collisions. So first we have the electron distribution function. So the red dotted line is basically the reference without any neutrals included. And the black one are the neutral ion collisions, and the blue electron neutral collisions. So we can see that for the most part, it's quite without effect, just there's let's say a very low population of higher velocity electrons going away from the wall in the case of the ionization, which we can see also here. There's larger effect on the ions due to the charge exchange and also ionization. So we can see that we get basically many more ions going away from the wall, which is obviously caused by the fact that when the neutrals get recycled, they're going away from the wall, then they get ionized or undergo charge exchange, thus become ions, and they still keep going away from the wall. And we can also observe that basically the effect of the charge exchange is larger than of the ionization. Then we can look at also the neutral distribution. So in the case of the ionization, there's really not any effect, but we can see quite a significant effect of the charge exchange collisions, where again, because the ions are about 5 times hotter than the neutrals, when the charge exchange happens, the hotter ions now become part of the neutrals, and they create this high velocity tail to the Maxwellian distribution functions, which we can see here also in the 2D distribution pictures. So at the end, we can just kind of look at comparisons of how the different kinds of collisions affect the analytical correspondence to the analytical formulas. And we can see that at least in this case, the errors are actually quite low. So even the analytical formulas give us quite good approximation. So the key takeaways probably here would be that when you're going to be making your BIT1 simulations and you want to have Maxwellian plasma, then you can achieve it through either Coulomb collisions if you have sufficient system parameters, or you can turn on the heating. We also demonstrate that the Coulomb collisions are nicely Maxwellizing, while ionization and charge exchange cause demaxwellization of the distribution functions, and that the plasma sheet as simulated by BIT1 agrees very well with the usual sheath theory. So that's everything from me. Thank you.
Questions, please.
Yeah, I have one quick question. I mean, you've showed loads of these like really nice 2D plots where you have your velocity distribution as a function of position. How did you make those? Did you have like loads of diagnostic points throughout the system to get like a spatially resolved thing? How, like, just because I really like that as a way of actually representing the data.
Yeah, so the distribution functions are currently given only per processor. So you need to run a simulation with many processors so that you get good resolution. And then in Python, you can just make these 2D plots.
So just so that I know, so you're basically saying I set one diagnostic like window like per core, or is it? DDF. Okay.
These are the
Right. Okay. Yeah. Okay. And this is just with, and this at slow equals 1, you get these files output?
Yeah, this is slow equals 1. These are the .fv files.
Cool.
But I mean, you can do it also with the movie. So yeah.
Hi, so thanks for the very interesting talk. I have a couple of questions. When you say the error on your simulations, I suppose that's so compared to an analytic solution.
Yeah.
Can you detail how you obtain this analytic solution, and actually, do you expect to recover the analytic solution?
I expect to recover the analytic solution if I have a good maxwellization. These are basically the formulas, right? The usual formulas that you have in Stang B. This is for the floating potential. And then I calculate the potential draw for the Debye sheet simply by subtracting the...
These are from fluid estimates.
Yeah.
But you're doing kinetics.
Yeah, but
So
if you have Maxwellian distribution, you would expect to recover fluid
fair enough.
results.
Okay, yeah. I think the second question that I have is, so you go over a few instance angles of your magnetic sheet, of your magnetic field line. First, I think you show 87, so that's like 3 degrees, very shallow instance. But in the second case where you talk about the recycling, you have, I think 60 degrees, so 30 degrees instance angle. This seems to be, to me, to be quite large. Is this actually realistic? Is this a toy model? Why did you change the incidence angle between the two simulations?
The change in the incidence angle really just was to speed up the simulations.
Yeah.
Like these simulations were performed as basically training for scrape of layer simulations. So they are really kind of, as you say, kind of toy models. And when you're doing scrape of layer simulations, like near the diverter, you would expect very shallow angles, right, of the magnetic field towards the diverter. So that was the reason.
Okay. How expensive are these simulations?
Where are we? So these were run on 3 nodes, overall 192 cores, and most of them between 2 to 5 hours maybe. The 12 is...
So you'd actually be able to run a scan over the instance angles to kind of see...
You can do it, but I didn't do it.
Okay.
But you can do it.
Okay. I think that'd be interesting. But okay. Thanks a lot.
Other questions?
Thank you, Simon. It's a very nice presentation with very good-looking results. I'm quite familiar with this because I've also done very similar simulations, actually the very same settings as yours in a recent paper with another PIC code. I just wanted to, maybe you know it, there's a very interesting paper by Procasin in the 90s in which he avoids doing the heating strategy, which is necessary in the unmagnetized scenario, by having a Maxwellian flux injection and a refluxing surface. So basically, you divide your domain by 2, you only simulate 1/2 of it. And every time a particle gets to the bulk of the plasma, it is refluxed. And this way, you avoid doing the heating. Maybe it's also interesting. I don't know if BIT1 can simulate that, but you get exactly the same results and half the domain size.
Maybe I answer this. Actually, we started with this 20 years ago, but this double bounded case is much more reliable. We have paper about this. The problem is you can easily estimate injection fluxes when you have a relatively simple case. The problem comes when you cannot we cannot estimate what should be injection flux for ions and electrons.
Yeah, of course. I mean, that's totally right. But for a simulation of analytical formulas, you can do that and you get very good fittings, very good results without having to do a heating, because also selecting the frequency of heating is something that is not... I mean, you can do simulation to see when you get a Maxwellian, but you don't know a priori. While if you do refluxing, you have it automatically. You maintain the temperature and you can do comparison with analytical formulas directly.
Yeah, but once more, this is valid all for simple cases. Whenever you want
Yeah,
to
if you have a generation of plasma in a volume, it's true. I totally agree with you.
So please let me finish. So this is simulation was done just to train, let's say, I mean, for simulation of scrape-off layer. In scrape-off layer, you have really heat flux, which goes through the separatrix. So it's exactly model we want to know. The first simulations we did really with this, I will present now a few minutes later. So it was a half system. So we are injecting, and it's really perfect. You get exactly analytic results. But whenever, for instance, you switch on neutrals, it's different. So you have to adjust. There are different methods, approaches, and we simply find out that it's much faster and much more reliable if you have a double bounded plasma for sheath simulation. You are simulating two sheaths. You can also at the same time have a different current regimes, different biasing. So in one simulation, you can even do two separate cases, and it worked better. Of course, the price you pay, it's not exactly, let's say you have some errors, but I will not call error because in reality it's not so full Maxwellian. So you can reduce this error as much as you want by increasing number of particles and by increasing heating parameter also. But the idea was not this. So we somehow stopped sheath simulations and we switched to either collisional sheath simulations when you don't need these, you have high collisions, or for scrape-off layer simulations. And so this is it just for training, which still shows that direction where you have to go. So you have to have heating and but try please to do now, if you put now neutrals and add now multiple ion species like we have it, because we have to include the impurities, and it's really very difficult. You will get definitely, you will not recover with high probability the classical sheath parameters, because you will have a kind of sheath, I mean source sheath, which is artificial.
Yeah,
because you don't
that's
know.
true.
Yeah, so this is, so our suggestion was all times to use, and this is much stronger because this sheath is non-quasi-neutral, so it accelerates at the injection ions. So we decided to go with the double-sided. In this case, you never had a let's say non-quasi-neutral region in the inside plasma. So it's because these forces are so strong that plasma forced to have quasi-neutrality, and
yeah, but actually in the refluxing case, you don't have a non-quasi-neutral because you are doing just refluxing and imposing a Neumann condition, the potential on the plasma boundary. There is also an approach which actually reflects with a numerical shield. But what it's true is that you get a quasi-neutral acceleration until you reach the sonic condition in close to the upstream boundary. But yes, I agree with you. It depends on what you want to study. If you know in advance the fluxes that go to the wall, which is not your case, you can do that. If you don't know that, you have to do double-sided. That's totally true. I agree with that.
okay.
In any case, we can do some nice benchmarks also, because I can also do the double-sided simulation. So
Yeah, I mean,
so I think it's a good benchmark between two codes. Can be done.
But I can add that BIT1 has quite complex, sophisticated, half-sided, half-bounded option. So some of them I deactivated, we will never use, but of course you can inject and reflect particles at the half, but like other people do. So it's also doable. But I mean,
we can do both. I mean, it could be done a benchmark in both scenarios. I mean, also double-sided is okay, I guess. Well,
good.
thank you very much.
Thank you. Okay, Yene. Okay, then we thank you once more. Simon, yeah. I will try to make a very short presentation about future plans and just in general about BIT1. So where from this name comes and what are the plans for multidimensional cases. So BIT1, so one-dimensional. Why one-dimensional? Why BIT1? Yeah, I didn't share it here. Sorry. So BIT1 comes from the names of the cities. So B is Berkeley, because it's based from Birtzal's group in Berkeley. So it speaks XPDB code. Then I is Innsbruck, where I was working when I developed this code, and T is Tbilisi, where I'm from coming. So it was nice names. So I assumed that we left it BIT1. And the presentation which I give, it's mainly coming work done by me and Mr. Kang, just our collaborator, so Eurofusion high-level support team. And so he was developing the Poisson solvers. And I want to say, very often people say, why you do 1D, why not 2D? Then I want to say I started with 2D. So my first simulation of sheaths was done by 2D, and it was XPDB2 code, and it was done in 1999. So actually, test simulations were done in already 98. So it was good result already because we started fast electron effects on the potential diver plate. And also the scrape-off plate simulations we did already in 2002, so we published on 2000, but presented was 2001 at the PET workshop. You can see output of the simulations, the radial profiles of the pressure, density, and temperatures of electrons and ions. Actually, in that case, we simulated comparison between, this was, to my knowledge, the second worldwide simulation of two-dimensional simulation of the scrape-off layer by full kinetic code, full PIC code, and was comparison with full kinetic code, direct one. And for the fluid code with a B2, which was predecessor of the SOAP-CETA code, and this XPDB2 was used, so actually updated XPDB2 code, which was kind of, predecessor of BIT2. So when I made this simulation, I say it's very nice. It can be very well submitted for different projects, but I realized that it's not a good idea because the physics you resolve with 2D, at that time at least, was not so sufficient, at least for the particle in cell simulations. And then I come back what Jakub was saying. We cannot resolve full-size machines, let's say large case full-size machines. So we can resolve compass, we can resolve Castor, but whenever we go to, let's say, JET, ASDEX, compass upgrade, ETA and demo especially, we need shorting, which was already described. I thank Jakub for this. I don't need to describe once more, but very important point. If I take one-dimensional plasma along the field line, there is just mathematically, you can easily show that if you make a transformation that you squeeze time and space, so to divide by some factor larger than 1K, and also same time increase the collisionality as well as the sources, it's absolutely invariant. So it means that you can have a region inside plasma which is invariant against this transformation, but whenever you are coming to the wall, as it was already mentioned by Jakub, you cannot do it because you're not full size without shorting plasma wall interaction. So you have this transition. So I don't want to spend more time on this because it was already described. I just show the examples. So this is a compass. So this is a density from the inner diverter to the outer diverter. So you can say two walls who are not very familiar with tokamak geometry. And this is compass. So no shorting, so it's K1. Then you come to JET, you need shorting, I needed shorting 10. And you have ETA, you need shorting 20. So, and these are more or less reasonable time you spend for simulations. And you don't see any principal difference in results, so you get what it should be. So these are good numbers. This transition area somewhere, it's so small compared to, so this area is so small compared to a large, compared to a whole scrape-off layer, that it's practically negligible. The exception is compass upgrade because anyway, small machine, and we are, so JET is 3 times larger than compass upgrade. So whenever you're using the same shorting, then it matters, as we see. For JET, it was not the case. Anyway, so the shorting works for 1D more or less. The problem is it doesn't work for 2D and 3D, because if you now put this transformation in 2D on 3D, so this is transformed equation, so this is Fokker-Planck equation 2D or 3D. you have this parameter. So everywhere it cancels. So this ain't transformation, but everywhere it cancels except this Lorentz force case. So it means that in order to make really correct transformation, you have to also change magnetic field or do something else. But anyway, so the easiest what comes in mind, you have to make transformation in magnetic field, but then there is no gain. So if you increase magnetic field strength, you first of all, you will have problems for the plasma-wall interaction because it's different plasma-wall interaction. Second, you have to satisfy condition for the time step. So time step should decrease accordingly. Usually this is main, one of the main, let's say, conditions that cyclotron frequency. So cyclotron frequency time step should be smaller than 1. Usually we take 0.35 because it guarantees 1% accuracy. So if you increase this by K factor, of course, you have to decrease time step. You do not get such much gain. So it means that in principle, we can do these simulations, but we have to keep in mind that we still make serious, like some kind of mistake at least. Contrary to 1D, 1D is practically no, I mean, we do not sacrifice anything. Unfortunately, many of 2D codes, including my simulations, are quite large. In my simulations, this factor was about 10, but you can find some, I don't want to name, so you can find this factor is 100 or even 1,000. So in reality, simulator is so very small 2D tokamak, but this is not, so this parameter is not properly resolved. Yeah. And then at that time, this is my invited presentation in Japan. So, and that time I just draw our capabilities. So I was simulating low density machine, and I said we need 10 to 8 time steps. And this was a realistic sketch. If, I mean, depending on the teraflop speed of the machine, what we can resolve. And it was clearly shown that in order to simulate 2D scrape-off layer, we still can do, but you need really whole machine at that time at least, and you need 1 week. But there was no even mentioning about 3D. It was impossible. So the idea was now to concentrate on 1D and still build 2D and 3D codes, which will be easy to then applicable to better machines. And actually, both codes were developed. So this is BIT2. So geometry is quite similar. Contrary to 1D, now we have in 2D, you have a walls here. So it's a diverters. Actually, diverters can be not necessarily whole wall, can be sections, but it has much more options as of you can have a fueling, impurity seeding. You can have different diagnostics here, including some really synthetic diagnostics. And this was tests which was presented quite a long time ago. I think it was 2016 at the PSI. So this is first test usually when you have a full code because omega plasma should be resolved, and you see the omega plasma result here in these simulations. Also, these are diffusion, the checking of the diffusion routines, so showing comparison with analytic one. You don't see difference because it practically agrees. The problem was different, the simulation time. The problem was the Poisson solver, which was developed under high-level support team. It was quite competitive These were competitive projects, so we were lucky to get 4 projects on sequence, showing that we need it and it's important. And then finally we got the Poisson solver. It's a multi-grid based done by Mr. Kang. So Kapseok was a very good collaborator. The problem was in order to keep very high scalability, then later it was done initially for 2D and then it was updated to 3D. And the idea was that we needed to have squares. So each core has to simulate square or cube if it was 3D, while the PIC rest was using the 1D decomposition. So it means that because PIC required, so the rest of the code required 1D, you could just construct this one-dimensional, very long scrape-off layer, which is, of course, you can make nice simulation, but it's not really real because it's very narrow. So and I realized that in order to really make compatible, I have to go from 1D to 3D decomposition or 2D decomposition. It's nightmare because you have 1D decomposition, which is very fast, even for 3D code, it's very fast. You have two neighbors, left, right. So the change of the, the transfer of data is in just two directions, and it's really fast and very high scalability. But then we see that in order to keep highly scalable, let's say, Poisson solver, we had to go to 3D or 2D decomposition, and then it changes everything. So now, if you have 3D decomposition, each core has 26 neighbors. So you have to change data with 26 neighbors. But this is not the whole story, because code is very optimized. I mean, the idea was to have very optimized. So for each case, so depending, for instance, if you have a wall here, if I come back, if you are, let's come here. So if you are here, so there are cores which are simulating this area. Of course, their solvers have to be different because there is a wall, and you don't want to make many if questions. So you have different solver for this. Different if you use an inner sol. Different if you have a corner core, so it simulates corner, so it's different. Different if you have a core which overlaps this fueling area. Different if it has a synthetic diagnostic. So in reality, for almost each routine, you need to have 26 plus different versions corresponding to each case. So what is the code was doing? So it analyzes to which are the most optimal solvers for this core. It was nightmare, but you need to sit down 1 year and it was done. But there was no time to couple this code with the Poisson solver. So I gave up because we switched to we had still a lot of requests from BIT1. So BIT2 is not done for BIT2, and I'm afraid it will take really very serious work to make from 1D decomposition to 2D decomposition. So for BIT3 is done, but especially taking account that probably we are successful is 1D, and one can think we can maybe come back to BIT3 and we can do it. The problem is, once more, I didn't check, I didn't couple, so we have good PIC part, good Poisson part. You still need coupling, a lot of tests, because this usually I don't like without testing. So especially here, I just plotted 2 cases for 2D codes, but I have about 20 test cases, because you want to be sure that each routine works properly, and this is, otherwise it's very expensive. So these are simulations you start. Imagine if you need, in average, 10 million CPU hours, in average for, let's say, productive run in 1D, so how much for 2D and 3D? And we are already, we are record makers probably in Eurofusion machines, so we are using it. But this is reality. If you want to have, let's say, full kinetic simulations, full resolution of atomic and molecular physics, this is price to pay. Yeah. So with this, I will stop. This is future, because as soon as we succeed with BIT1 and we somehow say, okay, now we do not have major developments in this code, we switch to 2D, probably with 3D, because it's better to directly go to 3D. Yeah. Thank you very much. So if you have questions, I'm happy to answer. Okay, no questions. I don't see if there is someone from outside answering questions. Okay. Please, yeah.
Yeah, just a quick question. Which kind of solver do you use for the 1D? Like a multi-grid or?
Multi-grid, yeah. Yes, multi-grid. It was really tough work, because really 4 times continuous, so it was done. So my request was it should stay, I mean, 10th of second, I said, because we are simulating, at that time I said 10 to 8. This was order, so each time step you need for simulation of the solution of Poisson solver, one had to, I said, I don't care how many cores we use, but its time should be below 0.1 second. Otherwise, there is no reason to start simulating. And this was satisfied. It was very difficult, but it was done. Yeah. But this is, you are right. I mean, the bottleneck of massively parallel kinetic simulation is Poisson solver. in a strange way, not the Maxwell equation solver, but Poisson solver. Yeah. Okay, as I see there are no questions, let me stop here. And we can move directly to discussion. So my proposal is to continue asking questions to Jeremy, because Kalia had questions. I had some questions, if Kalia is still here. And then we continue discussion.
Yes, David, thank you. Basically, I asked the question to Jeremy offline, but maybe we can discuss it as well. So my question was because because Jeremy showed an overhead for the flattening of the memory. So my question is, in case we change the memory alignment in the entire BIT1, then this overhead will be non-existent, correct?
Yes, that's correct. Yep. Can you heard that?
Yes, Jeremy, thank you.
Yes, that would be correct, because what you saw and plots, maybe if I share the screen, David, should I?
Yeah,
share?
please.
Come
Yeah, please, of course.
Give me a second. Give me a moment. I'll just share the slides again.
Yeah.
I'll share it. So David, I have a PDF version, so I'll send you it. I'll just open this one.
Yeah, just you.
Yeah.
Just before Jeremy shows, okay. Presenters, please send me, those who didn't send me your presentations, because we will spread it to the registered participants. Yeah.
Kali, can you see the screen?
Yes.
Okay, let me see if I can go to that. Let's just go up and down. Okay, let me see if I can go to it. Yeah, I'll go directly to the results. Yeah, this one.
Yes, exactly.
Yeah, so this is very, this is actually the most crucial slide. That actually the reason why we went ahead and used the other slides, where the weak scaling and so on and so forth. But what does this show is that or this BIT1, where you see it says 4 ranks and multidimensional, that's actually BIT1 running with 2 times the amount of time steps. So we used around 200 time steps originally. Didn't want to use too much time steps. And because the GPU was so fast, we used 20 times that amount to get some numbers, because it was literally 0.00. But what do you see is this red part is the cost that you mentioned when we use the one-dimensional continuous array with BIT1, the mover, and the RJ. So you're totally right. If that, if the whole code uses the 1D, a continuous array, you won't see this red box. And if you look at the OpenMP version, the implicit version, and then the asynchronous version, you'll notice you still see these red blocks. Why is that there? That's because I'm actually optimizing the transfer with OpenMP. So that's why you still see that red there. So that means that well, I have a measurement for that. I'm not showing it here, but it's just showing you. You see, it says 24 seconds. So that's how much amount of time being saved from 298 seconds all the way to 24 when I optimize it. So that actually will save us an additional 24 seconds if we remove that extra cost.
Yes.
But again, what you see is, well, if you look carefully, if you notice that the blue box is the other functions. Because of the flattening, we still have overhead, right? Because it's on the main. So the BIT1 1.c, that's still on the main. So if you look at, compared to the CPU version, the blue box is still smaller, right? It's because we still have overhead happening when we actually flatten as well. So it's not only affecting the mover, also affecting the other parts of the code as well. So you're right. You're right. If we do decide to go directly with this data layout, we won't have these extra layout. Actually, it might be even faster. We don't know because the overhead could be even more.
Yes.
Yeah.
Yes. Okay. Perfect. Yes, that was my thinking. Just wanted to make sure which layout you're using for the entire thing. Yeah. Okay. Thank you very much.
Perfect. Yeah. Another question? Yeah.
Yeah. A quick comment on this slide. So for the baseline execution time is just 4 MPI ranks without any threads or MP threads.
That's just MPI application. So just
okay,
MPI.
But only 4 MPI ranks, right?
Correct. Yeah.
Okay. Yeah, I mean it's always a bit tricky to do this kind of comparison because eventually you might end up comparing, I don't know, apples with oranges, kind of.
Yeah.
But especially when you go to GPUs, I might suggest to do a comparison with full node CPU, because I mean, GPUs, especially Grace Hopper, are quite beast. So comparing 4 MPI, just 4 MPI ranks with 4 Grace Hopper is, well, I don't know if it's really meaningful actually. Because I mean, you expect this kind of speed up because actually the computational power per se is completely order of magnitude differences. So it would be interesting to see the baseline in which you take all the CPU cores in one node. That could be interesting.
Yeah. So what you see is the optimizing part. All of that are using the full node because I'm actually using the 4 ranks, and then I'm using all the cores on the optimizing part. But the other part of the code is still MPI, as you know, because we only, excuse me, we only optimizing the mover in this case. So the other.
Compare like the original mover with only 4 MPI ranks. I mean, it's not a fair comparison, in my opinion, comparing the mover with just 4 MPI ranks with 4 GPUs. That's my point. I think would be more interesting. Then eventually the problem is not the same because when you change the MPI ranks in BIT1, it changes a bit the problem. But in my opinion, would be more interesting to see the execution time for a full node simulation, like
you mean in terms of
like 128?
You mean of using 128 MPI ranks?
Yeah.
Now the problem here is that if you use 128 ranks, you're going to have MPI communication. That's going to happen because you're going to have more MPI ranks.
Yeah, but still, if you are on node, it shouldn't be so much important.
If you want to use, remember, if you want to use GPUs, as you know, we have to give firstly all of the GPUs at least 1 rank, right?
Yeah, but my point is that the computational power that you are comparing is not comparable. It's just 2 orders of magnitude completely different. So I don't have the plot here because I know what you want. What you mean is I'm not showing you the plot because Stefan actually asked this exact question. I'm not showing you here actually running the 28 ranks, MPI ranks using the full node, and it's actually still slower. Okay, no, exactly.
Yeah, but I'm not showing you here. So what I could do next, I could show you the plot. We could make a new plot of this, comparing the four ranks here for the first one, and then 128, which you're actually simulating in the Slurm script. Because I think what you're asking is you want me to show how much is the computational time if I use the full node, all of the MPI ranks. That's exactly the question Stefan asked, and I showed him the results, and it was faster.
Yeah, exactly.
Yeah.
Because I think, in my opinion, it's more fair because basically, for GPUs, it's full node.
So I think you mean similar to what we did with the CPU. We did the exact same thing.
Yeah, exactly.
This is what you want. Yeah. You wanted where I'm showing you a comparison of all the nodes, the complete node being used, and then I'm using just the 4 ranks and the 4 GPUs in this case, and the others as workers.
Yeah,
I don't have that actually on the plot.
No,
Yeah,
it's
but
fine.
that's
Just
exactly what you need. Yeah,
something that I think it's more
yeah.
interesting and
You're totally
more
right.
fair as a comparison.
Yes,
But
you're
still,
right.
then eventually you're
Yeah.
still comparing.
But that's
percent
exactly what Stefan, that was actually why before we were presenting today, we said, Stefan said, is this faster using the full node? Because that they're gonna ask. And yes, it was. I just didn't put it here, today.
Okay, thank you.
Yeah, you're totally right. Thanks for that. We'll try to present that.
Yeah, first of all, thank you very much for presentation and your advances. Yeah, just shortly continue what Luca was asking. Actually, this is kind of first attempt just to check approach. Of course, finally we need whole node and we need many more nodes because
you know, that's expected.
And of course, there's a huge difference. It can be problem is if it's not successful, this small number of ranks, that probably is not successful for large. So to my understanding, this is just testing approaches, what we have to choose.
Correct.
Then comes one node and then comes a multi-node cases. Finally, we have to have an exascale version. So that this is, I think this is the right way to go.
That's actually one of the reasons why I did the weak scaling, because I want to know.
But I mean, Luca is right. I mean, for 8, it can be ideal, but then it can go.
Yeah, exactly.
Yeah. So my point is, I was very surprised about this approach of a unified memory. I thought it does not exist at all, but now after discussion with you and with Stefan and Luca, it appears it's not so. So what is the price one pays if you use unified memory? So CPU, GPU are accessible.
So you do have a cost with the unified memory because you have also the overhead.
Is it squeezing memory size or it's
so you're still limited to the amount of memory the GPU can handle.
Okay.
Yeah, but you do also have overhead from using unified memory. It's technically better to use explicit in a case.
Left-hand side case.
Yeah, which is the left side, because you can explicitly say how you want the copying on the data to be performed. But what we wanted to see is it a little bit faster using unified memory based on using GPU, the GPU memory in this case. But you don't get this correct. With unified memory, you will have overhead. That's automatic for sure. It's just that in the BIT1 case, it was a lot more faster when we run the result. We did it, and we saw that the mover and was a lot more useful when it didn't need to do that much copying back and forth. You do have the copying in the back because it's still managed memory. You're still managing the amount of memory in this case, data movement.
Okay, thank you.
Actually, it says unified. It says unified, but it's actually managed.
Okay.
Yeah, it's just. Yeah, exactly.
Yeah. So it's easier. So it's
easier for the
to GPU. Yeah.
Yeah, it's easier for the GPU because you have to think now with porting. For example, when I was originally starting to port the mover, you know the what is it? The end mover is the end move, I believe, the end move function. So inside of a function, and if you have another function, you actually have to tell the GPU what is that function. So you actually have to define this function. So there's a way to do that in OpenMP and also CUDA or different versions. So I'll have to say declare this function exists in the code where it's like a pointer. It's like saying it's over there, and the GPU knows exactly what to do. So I'm basically defining what's inside it. So it's the same. And the same thing with the GPU part as well. One of the things, if you notice, when I use Monte Nostrum, it has around 64, I can't remember, 64 or 65 gigs or so. I'm not using all of that. We're using around 30, I think 39 or so gigs of memory. So we still have a lot of space to use. So it's really useful. Again, this is preliminary. For sure, you will have some overhead. I expect if we run a lot of nodes, we're going to have a lot more overhead. So I most likely will recommend going explicit. And then another thing I was thinking about, because it's still preliminary, right, is this here, even though the asynchronous is faster, there can be a kind of delay, a problem with a kind of overhead that's happening with the data, or the data can be incorrect, because I'm explicitly saying, I'm putting dependency clauses to say, okay, do not overlap, do not have any data race with kernels. So most likely the second one, where you see it's 116 seconds, might be more effective. It's almost like optimizing using the O2 versus the O3. Yeah. It's very similar. This was another recommendation by one of the reviewers. It's very similar where we presented, where we said the O3 is too aggressive. We're using the O3 is aggressive, and the O2 is a lot more useful. It's it's more accurate, and so on and so forth for us. It's the same way. So we have to decide, are we going to go asynchronous, or are we going to do not asynchronous in this case? But again, the point is, the issue we found is the data layout needs to change. Really, that's the...
But as we discussed, we know better what to do.
Yeah, exactly.
Jeremy, on this slide, you write 95.6 speed up is actually 95.6 reduction. So you have a 20 times speed up.
Yes.
So that should be corrected.
Yes, okay, I will update that. Yeah, thanks.
I realized I made some unnecessary overhead in this code, which will be fixed.
Yes,
so the 1D flat array is actually a copy of the multidimensional.
Yes.
And I will change this so that the multidimensional is a pointer map to the 1D flat. So there will be no more copy back and forth.
Yeah.
So the green part will actually shrink to nothing. The red part, sorry.
The red part,
will shrink to nothing.
Yeah.
So you'll get better speed up. So stay tuned for future plots.
So if you notice, that's why I automatically optimized it right away.
This was a rookie mistake. Sorry.
Here, I kindly ask to involve me in this discussion, because I was surprised when you were doing transformation, and I said, what Stephanie said, this is obvious way to go.
Yeah, well, it's preliminary, right? So it's like the starting point. Yeah.
We have to also test this for collisions, as I said.
Yeah. I mean, we still have the index, because we still have everything, I mean, so it's not an issue.
As Stefan mentioned, you don't need index because you can calculate it.
Correct.
Yeah. So from the having number of particles is to, I mean, it will not go to zero. So the red one, then you need to find out.
I don't think they can hear you, David.
The coding, you will need it. Yeah. So whenever you want to,
David, I don't think it's not on.
I think it's on.
It's on.
Yeah, it's on. Yeah.
So I had to rewrite the kernels for mover and arranger using the flattened 1D.
Yeah.
So in order to port other functions to GPU, they need to be rewritten to use the 1D, the flat array. Yeah. So that we can offload to GPU and.
So it comes to me, in other words.
Yes.
so at the moment, just move it in arranger.
Yeah. Okay. Yeah.
But for other functions, we have to think.
Can we make this discussion at the meeting in Dresden?
You mean the face-to-face? Yeah.
Yes.
Yeah, definitely.
I think it's good. Yeah. Because it's a long-term discussion, so one has to. Because meanwhile, because there are different versions because I'm optimizing now the non-uniform loading. So if this will be hopefully ready, then it's easier to implement more at one step and not to do it stepwise, different optimizations, different time. Yeah.
Yes, I will merge the different development branches to one development branch.
And then
this is kind of becoming private discussion. Now the question is, I mean, other questions to Jeremy general. So because. I think that's all. Other questions, if you have.
Do we have any questions online?
Last chance. I don't see from outside. Yeah, I have personal ask. In general, I mean, we organize many meetings. Yeah, but I mean, organizing training is more difficult because you need also relation with. Supercomputers, and so it's different. So this is probably my second training which I organized. But still, it will be very interesting for me and for next generation BIT1 team users to have your feedback. Please send to me your opinion direct without hiding. So what you like, we don't like. Otherwise, there will no improvement. Yeah. So, but it should be. Don't hesitate to write truth. What you don't like, especially this is important because if you like something is good, we keep it. So, but if you say, okay, this would, in your opinion, would be could be done better, send us. Yeah. Thank you very much. Jana, you have some.
I have a short question.
Yeah.
I remember this during Shimon's talk. So as I remember, he briefly mentioned that when you have the heating, you are now relying on a model that is basically based on the Coulomb collisions, right? Yeah. And previously you had like a very one-to-one case where you would just update the. So did you make, because I would imagine the Coulomb collisions are based on the relative velocity between the particles. So in case you would have a significant difference between the temperatures, in principle, you wouldn't be warming the cold particles. So did you, for example, it might play a role if you try to do something like Tongsuangmir, very simple model. Did you ever try to repeat these basic simulations with this new heating model?
I mean, majority of routines in reality have very long testing phases. So what I remember, what I did, especially for when I was doing a BIT2 code, very long tests of different models. And once more, I came to conclusion that big particle in cell codes don't like artificial things. So, and the best results, it means you spend more time because it's a real Coulomb collision. What you do is code is picking up this particle from actual distributed particle somewhere, so it's not a simulated particle. It collides your actual marker with this particle. And this was the best output because whenever I was adjusting just velocity, it was much simpler, or just forcing. And Coulomb collisions have advantage that there's a small angle change, so it does not make. So whenever you are doing small adjustments, direct adjustment, this was still causing some. PIC does not like it, so just
I mean, I would say that
oscillation level.
I would say that the previous model probably worked. You would maximize faster, but probably rougher.
Yes.
Now it takes longer time, but it probably gets the same result.
You do not really gain because it does for shear simulations. Maybe it's okay, but when you go long system simulation like scrape-off layer, when stability is one of the main issues. So then this was the best way. I mean, as smaller system you have, so shear simulations are relatively simple. Let's say much simpler than scrape-off layer because you do not have such stability issues. So you simulate few millimeters or centimeter, and in the case of compass, you simulated meter effectively, and with shorting factor, you simulate 100 meters. So stability. I mean, due to stability reasons, we did it, but it was long time, so it was really many models we had. We have also tested linear Coulomb collision model, which I described yesterday. It's also very fast, but still this was the best. I mean, I mean, we didn't try to investigate why, but just okay, this was best, and so it was cleanest output, so lowest oscillation level. So let's say,
okay,
this was the main factor. Yeah.
As a follow-up to Yerne's question, maybe is it possible to have multiple collision models in the code and activate them when we wish, so that we don't disregard them completely by not having the code inside?
Yeah, I mean, you mean have possibility to? I mean, which collisions do you mean?
For example, the old heating mechanism.
No, you. Of course, each particle has a relative heating. So there is so when you are switching on your heating, then you should go to, so in the main stream, so you are say, okay, heating is on. Then for each particle species, you specify separately then. You specify its relative heating. So and it can be less than 1, it can be larger than 1.
I meant I meant to have a physical routine, the physics, to have one using Coulomb collisions, that it's now existent, and to have another routine that uses the random particle, so not to use the relative velocity, but to use a random picking particle.
Yeah.
So, and then the user decides which one to use.
In principle, it's not difficult. I mean, if you go to particle heat per heat function, one can put there, but
I mean, to have officially, let's say, multiple routines, explain what they do in the documentation, and for the user to.
So why do you need this? The question is, what do
depends on the case.
Yeah, but
to
show
have
me one
flexibility.
case when you need, because you have two kind of sources in principle. So I need more.
For example, like Erne mentioned, the heating of the extremes of the distribution function is not happening at the same rate.
Heating of what?
Of particles in the extreme of the distribution function is not happening at the same rate as the ones in the middle because of the relative velocity.
Why?
Because the relative velocity is much bigger. It's much
okay.
bigger.
Okay. In other words, you want a collisionality which not dependent on the velocity.
Yes, velocity difference. Yeah.
I mean, actually, we are using it here, but I mean, it's quite simple. One can, it's trivial, can be done. You just,
So
it can be easily done. I will show how. But it's just you go to Coulomb collisionality. You just say, okay, it's inspired velocities. Put their thermal velocity. That's all. So it's doable. But I don't think that we are doing this. We are simulating now inverse sheaths. It was a headache for us because the original paper, we use this very simplified collisional model, so we wanted to adjust. So we are simplifying the down, down, down. I mean, reality is that in this Kraepov layer, it's a real process. So you really have Coulomb kind collisions. Yeah, kind of. It's better describes than. But if it's doable, if it's necessary, it can be done. I mean,
just have some flexibility in the physics that we can pick in the code. Yeah.
Yeah. Okay. This will be shifted at some point, but in principle, it's very simple. If you need now, I can show how to. We have.
I mean, It's not about having it now because I can implement it myself, but to be something that is always there for all users and it's documented and anybody can choose, like with some switch somewhere in the input file.
We are more egoistic. We first want what we want.
not to limit, let's say. Not
when we have time, we do for general. Yeah, but I mean, it can be done. Yeah, I mean,
So any questions for me? Maybe I don't know.
No, probably not.
No more. Okay, I'll stop sharing.
That's also.
And online, no questions, right?
But I think these suggestions you can send also via email, so we collect and we do it. So we are coming to the end. I want to thank you for coming here. It was a pleasure hosting you. I also want to thank the supercomputer, Vega and Carolina teams who supported us. Especially want to mention Mrs. Karina Pesatova. Yeah, sorry. She really helped a lot. I want to thank our team who prepared all these, and especially Ivana Svadlenkova was preparing our coffee breaks. And I wish you a nice trip back. Once more, thank you. And if you have some wishes and like Stefan say, send us to us and we try to satisfy it. Good. Thank you very much. Yeah.
Thank you very much. Very nice hackathon. Thank you very much.
Very nice. Bye.
Bye.